All right. So here we have a nice practice problem, finding out what mass of sodium carbonate will be neutralized by 25 milliliters of 3.1 molar HCl. What goes to the right of our equals sign, Fred?
Um, Grams of sodium carbonate?
Yeah, good. Grams of sodium carbonate. Okay. And what are we going to start with?
Um, the molarity of the HCl?
Yeah, that sounds good. 3.11 molar HCl. That means moles of HCl for every liter of solution, right?
Yep. And then change that liters to milliliters?
Okay. Or is it okay if I go like this, 0.025 liters? That's 25 mils. Is that okay?
Yeah, okay. That's all right.
Okay, good. Let me fix your hair there, Fred.
Oh, thank you.
So now we're in moles of HCl, and I can convert moles of, or I can relate moles of HCl to moles of what?
Sodium carbonate?
Good. Moles of sodium carbonate. We have a chemical reaction. Oh, no, we don't have a chemical reaction.
I just know what it is. It's 2 to 1.
You think so? To what?
2 HCl's to sodium carbonate because there's 2 sodiums for every carbonate. The carbonate has a -2 charge.
Okay. So let's double check, see what you're saying here. If we're combining HCl with sodium carbonate, the products are sodium chloride and H2CO3. Is that what you're talking about?
Yeah, so to balance that, you need 2 HCl's.
Okay. That's where you got the 2 moles of HCl for every one of those. Okay, got it. And then we go from moles of, wait a second, we want grams on top. Oh, we want grams of sodium carbonate. So we go from moles of sodium carbonate, Na2CO3, to grams of sodium carbonate. And that is 106 grams for every mole. Okay, so 3.11 times 0.025 divided by 2 times 106. Did you get an answer?
Yeah, is it 8.24?
Oh, 4.12. Oh, did you divide by 2?
Oh, I didn't divide by 2.
Okay, good. All right, ion concentrations. Now, conductivity is an important parameter that we're often trying to keep track of, and it's related to the ion concentrations in solutions. You put salts, ionic compounds, into solutions, and what happens?
They dissociate into their ions.
That's right. And if it's sodium chloride, for example, then you would get 2 ions resulting, right? So if I put some sodium chloride, for example, 1 molar sodium chloride, if I made a 1 molar sodium chloride solution, that sodium chloride dissociates into sodium ions and chloride ions, right? And the concentration of ions uh, would be 2 molar, right? So if I want to identify the concentration of ions in a solution, and well, let's say I have a 0.1 molar sodium carbonate solution, right? I need to know the concentration of ions. That's in molarity, so that's moles of ions for every liter of solution, right? Um, what I can do here is I can relate the moles of Na2CO3 to moles of ions. And for every Na2CO3 that goes into solution, I get 2 moles of, sodium ions and a carbonate ion. Okay, so that's 3 moles of ions for every 1 mole of sodium carbonate. So the answer here would be 0.3. See how that works?
I think I follow that. Ions just multiplies the concentration by how many ions would result when it dissociates.
That's right. Very good. So if I have a zero point 0.6 molar barium chloride, what's the concentration of the chloride ion?
Oh, just the chloride ion?
Yeah, sometimes they'll just ask for one of the ions, sometimes they ask total ions. But here, what would the concentration of the chloride ion be?
Twice as much, 1.2 molar.
Very good, 1.2 molar. Okay, another important concept is the actual yield compared to the theoretical yield, right? And identifying our percent yield. Now, you guys might have done that before in lab. Have you done that before?
I think we did do a little bit of that stuff.
So, when you're performing a reaction, because of the stoichiometry and the amount of material that you add, we can predict how much product we should get. But we don't always get that much product. So there's the theoretical yield, how much product we should get, and then there's the actual yield, how much we actually end up getting. The percent yield is this actual yield divided by the theoretical yield times 100. Okay, so for example, you make cookies. You ever make cookies, Fred?
Yeah, I do that. I do that on Friday, Saturday nights. It's a good fun time.
Yeah, you invite friends over and stuff.
Yeah.
So if it says you're going to get 36 cookies, but you only get 24, right? The percent yield would be the 24 divided by 36 times 100. You follow that?
Yeah, I get that.
So if 6.4 grams of methanol was mixed with 10.2 grams of oxygen and ignited, and we get this much carbon dioxide, we want to know what the percent yield was. Okay? And we should be able to identify what the theoretical yield is. Here, this 6.12, is that the theoretical yield?
Yeah, that's the theoretical yield.
Well, we don't necessarily know what the theoretical yield is yet. We just know that this is what we actually got. So that's what we call the actual yield, right?
Oh, yeah, okay.
All right, so the theoretical yield we have to calculate using the 6.4 grams of methanol and the 10.2 grams of oxygen. All right, so now this is another kind of a problem which we haven't introduced yet, but is very important. It's called a limiting reagent problem. Because notice in this scenario, they're telling us an amount of this and an amount of this. Usually they just say, hey, if I put in this, how much of this am I going to get? Or they say, if I put in this, how much of this is going to be required, right? But now they're saying, if I have this much of this and that much of that, how much product can I expect? So we have to do the calculation twice for the amount of carbon dioxide that we would expect based on these masses of the different reactants. And that's called a limiting reagent problem. They might give us different numbers, and if the problem's perfect, if the amounts are perfect, then they'll give us the same number. But usually, in a scenario like this, the amounts will be at least slightly different, and we'll get slightly different amounts that are theoretically possible. All right, so what we want to do here is say how many grams of carbon dioxide would we expect to be able to get if I started with my 10.2 grams of oxygen. We can do the 10.2 grams of oxygen here. I'll draw another one down here where I'm looking for grams of carbon dioxide if we start with the 6.4 grams of the, I'm just going to call it methanol, okay? So we can do the oxygen one first. For every 32 grams of oxygen, that's a mole of oxygen. Why do I want to go to moles of oxygen?
You can use the power of the equation.
That's right. The stoichiometry allows me then to relate moles of oxygen to moles of carbon dioxide, which is 3 moles of oxygen gas for every 2 moles of carbon dioxide produced. And then I can go moles of oxygen or moles of carbon dioxide to grams of carbon dioxide, right? 44 grams for every mole. Okay, so calculator, 10.2 whoops, oh, I'm going the wrong way, there we go. 10.2 divided by 32 times 2 divided by 3 times 44. Okay, so my answer, oh, what happened there? 10.2, oh, we have a decimal point there that doesn't belong. 10.2 times, or divided by 32 times 2 divided by 3 times 44. So we got 9.35, and that's theoretically how many grams of carbon dioxide we would get if what?
If you had that much oxygen?
That's right. This is if I had that much oxygen, that's how much carbon dioxide I would get. Nowhere in this calculation does it say, and if I have this much methanol, right? It's just if I have that much carbon oxygen, that's how much carbon dioxide I'll be able to get. The second calculation here is going to go take us from grams of methanol to grams of carbon dioxide. And I can go grams of methanol to moles. Again, why do I go to moles?
Because then you can relate the stoichiometry to the moles of carbon dioxide to methanol.
Very good. Moles of methanol, moles of carbon dioxide, and then moles of carbon dioxide to grams of carbon dioxide. And there's 44 here. We already did that. What's my ratio methanol to carbon dioxide?
2 to 2.
Okay, good, 2 to 2. And I could do 1 to 1 there as well, right?
Oh, yeah.
And then 32 grams, 32 grams of methanol. Oh, no. What's the mass for the methanol?
They didn't give us the molar mass of methanol.
Okay, so we have to find the molar mass of methanol. I can do that over here. Molar mass of methanol.
Isn't it 40?
We'll see what it is. I think it's 60.
What's going on?
I don't know why it's taking so long. Let's try again. Is our internet down? Molar mass of methanol. 32. Oh, it is 32. 32 grams per mole. All right. So 6.4 divided by 32 times 2 divided by 2 and times 44. All right. So 6.4 divided by 32 times 2 divided by 2. I'm going to skip that part. Times 44.
8.8?
Yeah, 8.8 grams of carbon dioxide.
So do we add those together?
No, this is how many grams we would expect if we consumed all of the methanol they provided. This is how many grams we would expect if we consumed all of the oxygen. Would we actually be able to get 9.35 if we consumed all the oxygen?
I guess.
But we only have 6.4 grams of methanol. So we see that the amount of carbon dioxide that we're actually going to be able to get is going to be limited by the methanol. So we're never going to be able to get that much because our methanol is the limiting reagent. So 8.8 grams becomes our theoretical yield. And then we can divide that by the, divide that by the 6.12 grams and times 100. And then our answer, oops, what did I do there? Divided by 6.2. Oh, 6.12 is how much we actually got divided by the 8.8. And then times 100. So 69.5, 69.6% it looks like. So our answer is going to be D. Okay, good.